everyone, and welcome to this episode of the Tangent Podcast, which I've decided to name It's Turtles All the Way Down.
I love it. I was thinking of a good one, and I love it. It's Turtles All the Way Down.
I might shorten that a little bit, because it's a bit long, because typically for Blue episodes, we call them On the Topic of, and then whatever our topic is, and you'll introduce that in a second, but I think...
On the topic of turtles?
Well, I think the fact that we're doing a book club today, having like on the topic and then putting the name of the book, would have been really long. So yeah. I needed a kind of short, sweet answer. But anyway, to introduce us to what book it is that we're doing book club of.
Yeah. So we will visit that later because we are discussing, and this came from a private conversation that we had, Anthony and I, on A Brief History of the Universe by Stephen Hawking, the late Stephen Hawking. This is actually...
No, A Brief History of Time.
That's what I said.
You said A Brief History of the Universe. The other one is The Universe in a Nutshell.
Oh my god.
That's the second one. The first one is A Brief History of Time.
We're talking about A Brief History of Time.
We're professionals here. We are talking about...
When you hand me a book that has both of the titles of the two books it contains on the cover, it's very confusing. But we're talking about Stephen Hawking's A Brief History of Time. And this came from a private conversation that Anthony and I had in regards to a question that I asked him about quantum mechanics. Casual quantum mechanics text message I sent you like at 10 o'clock at night.
Yeah. Listen, I will take any excuse to talk about quantum mechanics.
Anyway, so he said, well, let's read this book. Mm-hmm. And we'll talk about it on the podcast for an episode. And boy, do we have things to talk about today. So let's start with the table of context. And since you're the one who has read this book more than once, I need to go back and read/listen to it again.
You do. It's not the kind of book that you just, barrel through and then say, all right, I did it. I made it through the whole thing. There's a lot of different, not niche, but very intricate ideas, and to touch upon a little bit of like the conclusion or the things that Dr. Hawking touched upon. There's a point in the book where he makes this statement and this idea that even in the sciences today, you can't know all of the sciences. Like, you have to specialize in something, and there's a lot of different parts in this book that go deeper into different specializations, even between quantum mechanics, relativity, even special relativity to general relativity are like pretty specialized. The uncertainty principle, black holes, all that sort of cool stuff, and cosmology and quantum mechanics and gravitation. And I thought it was a good book to start on to anyone who wants to take a more serious journey into quantum mechanics, because let's be honest, I've heard a lot of people who are not part of the scientific community, for lack of a better way of putting it, people who have not actually studied quantum mechanics talk about quantum mechanics. I am not an expert on quantum mechanics. I just know a good amount of the theory because I studied it in school and other things, and I've read about some of the topics in my own spare time. But I would, I'm not a doctorate. I don't have a doctorate. I don't have a doctorate in those fields. I'm just, an avid hobbyist. And I've heard people kind of mangle the different theories of it and think about things that scientists might say about some of the theories, and they might just take those ideas and run too broadly with it. Mm-hmm. So I thought it would be good to get a good foundation and basis from someone who's a professional or was a professional in these topics. And I think that Stephen Hawking does a really good job of doing it. Having said that, there was a point that you brought up to me, which I can agree with. As, I guess, an overarching disclaimer, not really a disclaimer, but just points of our own personal contexts. you have a deeper theological background than I do. And in the book, at the beginning of the book, that theory of, and you might have the exact quote of how he says it.
I do.
That there's a God or whatever is just dismissed. It's just whatever, because having a bit more of the context, I can understand him dismissing that casually and not really take much issue with that. But I understand the point of what you're saying of someone who wants to read the book from outside of this scientific community, for lack of a better way of putting it, and maybe not taking that dismissal as easily as I might. And
right. So this whole thing came about when you get to about chapter 4. Chapters 1 through 3 I was really enjoying, because it's a little bit of a history, it's a little bit of scientific context on how we get to the place where Stephen Hawking is going to start hashing out his theory. And they start talking about the uncertainty principle, which is there is an inherent uncertainty in the act of measuring a variable of a particle, meaning that you can go back in observation further and further and further, but at some point you can't see far enough back, and so therefore you just have to be okay with not knowing. So you can explain things up until a certain point. Now, in chapter 4, when he talks about the uncertainty principle, he was acknowledging, and he did acknowledge, that up until the point when speaking about the beginning of the universe, whenever the question of what was before the beginning of the universe, or what was the state of the universe pre the Big Bang, even scientists back then, in accordance to the uncertainty principle, were okay with just saying, and God created it. Okay? And so he has this quote that says in chapter 4, we could still imagine that there is a set of laws that determine events completely for some supernatural being who could observe the present state of the universe without disturbing it. However, such models of the universe are not much interest to us ordinary mortals. And that's a statement that I took issue with. It's not the fact that he makes the assumption that there is no deity outside of our space-time universe. It's the fact that he states his assumption as if it's fact. This is an opinion. The fact of saying that, assuming that there is a divine being, isn't of any interest to us ordinary mortals. That's him stating his opinion as if it is everyone's opinion. And I don't like that. It's okay that he has an opinion.
Right.
Even in the theological realm, like I before we got on the record or whatever, before we started recording, I was telling you about a book that I was reading that was talking about a monotheistic, which is, for those of you listening who might not know, is the belief in a single God. It was a book talking about a monotheistic worldview, and it admitted that there were many traditions that believed polytheistically in many different deities, but that wasn't the purpose of the book. And so it starts the book with an introduction paragraph saying, I acknowledge that these other ideologies exist, but for the purpose of what we're going to talk about here, let's begin with the assumption that there is one God above all other deities who is more powerful than they are. Just kind of shoving all of that into a neat little box so that then they could hash out this other theory that without that question. And that's all that I was asking for. He makes another interesting statement, I think. I don't have the exact quote written down. It was either in that chapter or later on, or in a different chapter. It might have been in chapter 8, where he says that if a god was so powerful and could defy the laws of this universe in order to create it, why would he create laws within this universe? And again, if you're going to make the previous statement of let's not even talk about a god, let's not talk about a god.
Right.
Because in asking that very question, like when a mechanic builds an engine, he wants that engine to be able to run on itself. So he has to create mechanisms and machinery within that engine so that the engine can, once it's on, keep going without him having to come and be doing maintenance every minute. So it does logically make sense for a god who can, without being bound by certain laws, make something that is bound by laws so that he doesn't have to continuously keep us from blowing up.
And I think what this eventually comes down to, before we get back into the actual book, it's just scope.
Right.
It's just an argument of scope, which, like, you can't, if you're going to be talking about the book and the scientific theory and the laws and that stuff, you kind of have to start with this empty box, and that was the way that I had put it when we were talking originally. You start with an empty box, and then you start adding your assumptions from an empty box. And yeah, he just kind of dismisses it a bit too casually. He dismisses that assumption a bit too casually, and then references it again later. And I think a lot of, like, one of the reasons why he references that is because they're, especially when you're talking about the uncertainty principle in quantum mechanics, Einstein famously was not really with the biz when it came to quantum mechanics. He even has
talks about that in great detail. He talks about Einstein.
Every great scientist have their vice, have their weak spot. They're not perfect, and that was more than likely Einstein's, was his avoidance of quantum mechanics. But yeah, there's a quote from Einstein that says, "God does not play dice." So there would be no, it can't just be, there can't be chance involved in some of these things. And I think that's part of the reason why he touches on it again, that this idea of a god is because of referencing Einstein's background. But yes, he does do it a bit too dismissively. Outside of that one critique, though, you even said that there was a
it's a good book. It's a good book. And if he had made that critique, and then we'll move on.
Yeah.
If he makes that critique and just rephrases it and says, we already have a model of the universe based on a deity.
Right.
I'm going to move forward and try something new. And try something new and try to make a model of the universe that does not have one. That's, if he had said, this is the assumption that this book is going to move forward, and I can get down with that. I've read books written by people that of different, theological and doctrinal backgrounds of mine. I've read books written by witches and wizards, like real ones. I've read books by Buddhists and Taoists and all different philosophers and people who disagree ideologically with me. Right. That's not the problem. The problem is when you state even I have never stated my ideologies as fact. I state them as my belief. And then logically walk people.
Or to put it in a more scientific wording, my model that I'm going to build.
Right. This is my model.
This is my model.
And these are the proofs that I came to.
Right.
This model in.
Axioms of belief, if you will.
If he had stated that first thing in chapter 4 a little bit more like that, which is weird because he's a scientist, we wouldn't even be having this conversation right now. Right. We would just already be into the book.
Right. But yeah,
anyway,
disclaimer,
moving forward, there's
just to anyone who can align with those reasonings. What was the first?
The first one was who said we were going to talk about the formula with imaginary numbers, page 173.
Right, imaginary numbers.
Imaginary numbers, because that's the basis of how he draws out his formula for a boundless universe or whatever.
Yes,
however,
an expanding universe.
Expanding universe.
Also, just as a brief side note with what the uncertainty principle is, because you mentioned that you can only go so far back, and then it's muddy how you can measure it. That's not what the uncertainty principle is. The uncertainty principle is that you can't measure both a particle's position and velocity. You basically are down to a choice. If you want to know the particle's position, the wave's position, you can know that, but you can't know its velocity afterwards, due to the method of measurement. The method of measurement destroys the information of the other. And that's what the uncertainty principle is, or more accurately, that's what the uncertainty principle is. But anyway, imaginary numbers. I weep that that's their name. There's a really great YouTube video. I don't know if they still make YouTube videos anymore, but the user is Welch Labs, WELCH space Labs, and the dude goes into imaginary numbers at length. And actually, I forget who. It might have been Euler, who is a famous mathematician who did a lot of work with imaginary numbers, referenced them as lateral numbers. And so from now on, I'm going to reference them as lateral numbers and not imaginary numbers, because imaginary is a terrible word. And basically, scientists needed a way, or mathematicians really needed a way to reference the square root of -1, because there are a lot of interesting properties to this number that is the square root of -1. To anyone who doesn't know much about math, you can't do the square root of -1 conventionally. You can't take a square root of negative number. It doesn't work. However, you can use, if you instead just not call it the square root of -1, you just call it, I don't know, I, for example, and just treat it like a different number. That's just the number I. You can actually come up with a lot of different interesting ideas based off of that. So you can solve, what are they called? Polynomials. You can solve polynomials. Quadratic polynomials you can use to solve the quadratic equation, if you've ever learned that. You can get answers to these equations using lateral numbers. And on page 172, which I had you write that down, there's a really good table which basically says, or it's a graph really. And imagine a number line. To anyone who's listening to this, imagine a number line starting at 0, right? Counting numbers, really simple. 0, 1, 2, 3, however. And actually, not even 0, starting at 1. The easiest. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. Number line. Then you can introduce the number 0, which is, one of the later numbers to be added to the number line, actually, the number 0, because for some reason 0 is a hard concept. Then you go into the negative numbers, all right? So -1, -2, -3, however many. You can go into rational numbers, so your decimals, 0.5, whatever, all in the same number line. Well, imaginary numbers, lateral numbers, are lateral to that. They're perpendicular to this number line. This graph is a two-dimensional graph. On the x-axis is the regular number lines. So the negative numbers, the positive numbers. The lateral numbers are just perpendicular, the y-axis on that graph. You could even go orthogonal one more time orthogonal is basically perpendicular, but
there you go.
But not in 2 dimensions and generalized dimensions.
If I had to define monotheism, you definitely have to define orthogonal.
Orthogonal.
I was like, I've heard of that dinosaur before.
Yeah, it's just perpendicular in another dimension. So 3 dimensions. You can use the letter J to reference another dimension of lateral numbers if you need to, if you will. So a lot of the usages for lateral numbers is rotation. So she loves attention. My dog is demanding attention right now.
Anyway, continue.
But yeah, so that the mic picked that up. I heard that.
Oh, that's great. That's awesome.
Yeah, so there's a really famous equation, e to the theta I. It's just a way to do different kinds of rotations in the imaginary plane, in the lateral plane, I'll call it, which is that same XY graph where it's the real numbers and the lateral numbers. And because there is a very intimate connection with waves and matter when it comes to talking about quantum mechanics, that's why you end up seeing the lateral numbers a decent amount, is because you can use like rotations, circles, and waves are very linked mathematically. And that's, again, this is going to be more of an overview of some of these concepts.
Yeah, because the way that I remember to just, again, using a philosopher's terms to define scientific terms, and we're going to get to that at the end of this too. If I can just try to briefly summarize, the reason why Dr. Hawking used, or at least he talked about, why he was using lateral numbers / imaginary numbers in his equation of the universe was because you can't do math in a plane. Or you have to do it in a line. And since we don't live in a line, he had to jerry-rig something, for lack of a better term, and make something work conceptually. And that's why those numbers were utilized and not real numbers.
Right.
I know you hate that just as much as you hate the term imaginary numbers.
Regular numbers, and lateral numbers.
Got it. We're jiving. It was very like you just said, like Anthony just said. This is very like introductory. For myself reading it, there was a lot of concepts within this book.
Also, side note, I apologize to anyone, and I didn't really want to interrupt you, but I'm going to try to not be very verbose with my descriptions. I'm trying. I apologize if I do become a little bit too verbose. And
you're excited. You like math.
Esoteric.
Yeah, your math brain is.
But yes, I will try to
going crazy right now.
Intro stuff. This is introduction stuff. But anyway,
the book I found for myself was it introduced a lot of tastes for things, and I was like, I would like to know more about that. But it gave me a place to.
Have you seen Starship Troopers?
Oh my god!
Would you like to know more? You said that as the first thing that I thought of.
Don't.
Sorry. This is serious.
Don't go watch Starship Troopers. Just.
Or be like me and have it on in the background and just listen to the whole movie, have no idea what the movie looks like, and then go back and watch it and see the amazing special effects that movie has.
This is my disclaimer. Don't go watch Starship Troopers.
Would you like to know more? Anyway.
Yeah, it just gave me like a starting place for other things that I might want to go into. And that being said, one of the chapters, and this is why I like even the audiobook that I have listening to it on Audible, not a sponsor, but they can be if they want to, is that it lists the chapters out by name, which makes it really easy to navigate to. And I need to revisit the chapter The Arrow of Time. Because here's the thing. This is my assumption, and this is my personal pet peeve, and I will admit wholeheartedly, I've admitted to everyone, to you, to Karen, that this is just my thing and my own search for personal satisfaction. I have yet to meet a scientific person who can explain to me that the concept of time is a dimension and not just the measure of something's development and decay, because Karen corrected me, because we are not born decaying. I would say yes, every human is born moving towards death, but that's a depressive thought for another day. But when you're born, you develop.
There's a peak that gets hit at some point, and you have to rise to get to the peak before there's
you develop and then you decay. And to me, if we did not decay, I don't think that time would be measured in the way in which we measure it. It would be completely thrown off its axis. So anyway, that being said,
do you know what a second is?
It's no, I don't. That's the thing.
It's the amount of time that it takes a cesium atom to spin a certain amount of times. I don't remember what it is. It's like a large number. But that's how the second is actually measured using an atomic clock. It's measured based off the cesium atom.
But my point is that is how we measure a second. And in order to measure that second, we had to, or that passage of event, we still measure it by something happening. So what is time? That's my thing. And so there's this whole thing is that, and he even talks about how there are only 4 dimensions. There, within the universe in which we know it, which he calls space-time. There are 3 spatial dimensions: length, width, and depth. I like saying depth and not height because it's confusing.
It's more general.
It's more general. And there's one time dimension. And then he says there are no higher dimensions. Mm-hmm. Again, there's another blank statement that he makes that I think could be argued.
Or at least there could be more evidence to learn further.
Right, exactly. But he just states it as fact and not as this is the assumption that we're going with. Mm-hmm. And they list the fourth dimension, the time dimension, as just that, as time. And my personal self is I have never heard an explanation of time as a dimension as opposed to a measure of decay that satisfies me. So this is all about my own personal satisfaction.
Yeah.
This is my own and that is kind of, I think, what science should be. Like listen.
I mean, in a way it is, because science just comes from mysteries and problems and questions that you've asked of like.
And some people aren't scientific.
Why does it stop being so bright outside after a certain amount of time?
Right, but some people...
Because the sun goes down.
Some people are satisfied right with that. And that is where their scientific curiosity ends.
Right.
Some people aren't. And so they continue to ask and seek the question for their own satisfaction.
Yeah.
And people stop their study of any topic once they're satisfied.
Yeah.
And then they can let their own personal uncertainty principle take over. You like what I did there?
Yeah, I see what you did there.
Anyway, so
but yeah, that's fair.
I need to revisit this arrow of time concept, because I'll admit it, we were busy and I was pumping gas when he started talking about a cup falling off a table and shattering, and then both being shattered in the present and in the past at the same time. And if it was unshattered in the present and was never shattered in the future, then in the past, was it still a thing? And I was really confused.
Imagine a cup of water falling off a table and breaking into pieces on the floor. If you take a film of this, you can easily tell whether it is being run forward or backward. If you run it backward, you will see the pieces suddenly gather themselves off the floor and jump back to form a whole cup on the table. You can tell that the film is being run backward because this kind of behavior is never observed in ordinary life. If it were, crockery manufacturers would go out of business. The explanation that is usually given as to why we don't see broken cups gathering themselves together off the floor and jumping back onto the table is that it is forbidden by the second law of thermodynamics. To anyone who doesn't know the second law of thermodynamics, this says that in any closed system, disorder or entropy always increases with time. It's also a form of Murphy's law, things that always tend to go wrong. I don't know. That's one of the things that I appreciate about Stephen Hawking in his writing, is he's very, like, not jovial, what's the word? Like, lighthearted. There's a specific word.
There's a specific word that I know,
but I can't think of it. But yeah, he's very lighthearted. He's very casual, in a lot of different senses, which sometimes, like you mentioned, too casual. But otherwise, it's like, it's not verbose, like the way that I am sometimes when I talk about science. Yeah. It's like super, like, lightweight, lighthearted. Like, he's having fun. He's having fun writing this, and it makes me have fun reading it.
That specific portion that you just read out of the book right there,
yeah,
I was like taking someone's credit card back from them as they were telling me how much gasoline they wanted, and my brain broke. Like, I was standing there, and then when he got to the end of it, they were like, it's filled regular, and I realized that I was still holding their card in their window, even though they had let go of it. I was like, oh, sorry, my bad. So I do need to revisit that, because I'm not saying that I'm right, and that's all, and that all these scientists are wrong.
Right.
I'm just saying that I'm not satisfied with the explanations that have been given. Like, and I know you made this in jest / kind of seriousness, but the first time that we had that conversation, you made a statement to me, and the statement was, well, that's a lot of complicated maths. That's a statement that has been a serious scientific explanation that has been given to me when I've asked questions that I hate. Like you gave it, and that was fine. I understand what you were saying and what we were joking about.
Yeah.
But I hate when you ask someone something scientific, or anything, and you'd be like, well, that's just a complicated thing. It's like if you were to ask me about God, and I would be like, well, that's really above your understanding. Mm-hmm. That would piss you off.
Yeah, it's a very unsatisfactory answer.
And it makes me look like to you an idiot. And I've said this a lot, not to go off on a philosophical tangent, but I've said this a lot, is that biblically speaking, my belief system, and I will argue with other people who claim to follow the same thing as me, if they say that we're called or we are asked to have blind faith, they are absolutely 100% incorrect and should be backhanded in the face. We are asked to have faith like a child. There is a difference between those two things in a cultural context that actually makes more sense. A child doesn't have faith that is based in nothing. Like, we're asked to ask questions. We're told to put our trust in something that has proven itself trustworthy. Not to just, oh, well, God's above you and you can't understand, so just trust him.
Right.
Like, but there's reasons behind that. So for a scientist to give to me the same, well, that's a lot of complicated math, and I'm like, try me. Like, I would at least want, like what you did, you started writing it out with all of your imaginary numbers, right?
Yeah.
Linear numbers. You started drawing
lateral numbers.
And at least with you drawing it out, I was like, okay, so the equation exists in which
there's something there. I don't know what it is, but there's something there.
So then I at least know that your statements are based on something,
right?
And not, well,
they're not hand wavy.
It is
right. They're not hand wavy. That's the term that's used, is sometimes when a professor doesn't give an actual proof for something, they'll say, I'm going to give a very hand wavy definition of something. That's what it is. It's very much like, there's something, and to those who are just listening, I'm waving my hands very sporadically, or not sporadically, whatever.
Flamboyantly?
Yeah. But also, after that description of a cup falling off of a table, you get the statement of what is called an arrow of time. The increase of disorder or entropy with time is one example of what is called an arrow of time. Something that distinguishes the past from the future, giving a direction to time. I guess another something to someone who wants a good context in quantum mechanics. There are two kind of facets in this thing called thermal physics, one of which is thermodynamics, which is strictly just, I think we might have touched upon this last week, but thermodynamics is strictly, or sorry, not thermal, is strictly like macro observations and things that you can get from that. Things like predictions that you can make and that you can glean from that. So, for example, temperature moves from hot to cold, or sorry, hot air rises, for example. It's an observation. There's things that I can do with that. Statistical mechanics is the other part of that, which is very much just like, how do particles move? What are the reasons why this is happening? When you said hot air rises, there are things that I could do with that, and my brain's like go on a balloon ride. Sorry, this is the Tangent Podcast, so you should understand and expect. Yeah,
things.
Tangents.
So the only other thing that I had written down was actually what this whole journey began with, was the idea of the quark.
The quark? Yeah.
The quark? Yeah, not the
Not quirks.
The quirk.
We're not talking about.
We're not talking about
what's that anime?
Yeah, we're not talking about My Hero Academia where you get superpowers. The quarks and how they spin up and they spin down in this concept in which, and this is where my journey started when I asked him that 10 o'clock at night text about quantum mechanics, was this whole concept that the universe around us and even us either is made up of or has some sort of different energy signatures and is energy.
But what is energy?
Right, exactly. But and thus the theory of the quark, and not like Cyclops energy blasts.
Right.
Like,
I think what this might be slightly incorrect in the sense that calling the Earth a sphere is slightly incorrect.
I love how you just dropped that down.
What? The Earth's not a sphere.
I know.
It's a spheroid. But yeah, it would be more accurate to think of it as waves and particles, versus matter and energy, because like you can use those words, those words mean specific things, but when you're talking about like what is energy, it's more similar to talking about different waves versus particles, because they both do similar things, however they are conceived and they exist completely differently in how they interact. Waves, you start to get things like superpositions. I mean, you also get that with particles too, but that's more, I guess it's also more with light. But like waves specifically, you can get things with like superpositions. Things like a photon is a massless particle. So there's weird stuff that happens there. And yeah, so it starts to be more of like this dichotomy between particles and waves versus really matter and energy. Even though those are, proper terms to use, there are specific connotations that they carry that can get muddied, I think. I feel like I've heard them by people in the scientific community, outside the scientific community, kind of muddying what those terms are, because you can't, which is unfortunate, is you just can't go into the maths all the time with people, because some of them, like, as much as I love math, it is hard. It's not trivial.
It's not an easy thing.
And so you do have to kind of use these hand-wavy descriptions, and sometimes some things get lost in translation.
So that being said, because again, like, this whole book had one of the longest chapters was dealing with quarks, and it was in and of itself only just an introduction to get you to maybe study quarks in another book in and of itself. So if I was going to say, we would do a terrible job, I would do a terrible job, even more so, I know, to try to describe that. So I don't know if you have like if you can find it real quick, his brief description or definition of a quark. And I think that would be good for us to just to do, and then we can kind of wrap up our summary of a scientific concept, because that's what we're doing. We're summarizing a summary
for what, for quarks.
No. I mean, a brief history of time is a summary of a bunch of scientific things. Yeah. And we are summarizing this book, therefore we are summarizing a summary. Right. That's anyway. Read the thing about quarks.
Yeah. So I'm just gonna kind of go through this. I'm not gonna read it verbatim. But he talks about, up to 30 years ago, it was thought that the protons and neutrons were elementary particles. But then they realized that if you make things hit each other hard enough, they break. And if they break, that means that those things must be built of other things.
Real quick, not to interrupt you. You said up. It said up until what, 30 years ago?
30 years ago. This book was written, I don't want to say this book was written actually probably like 15 years ago.
15 years ago?
Let's see. Let's look at the copyright real quick.
Yeah. Look at the copyright real quick, because I'm just curious. I like time frames of things.
I mean, it is called A Brief History of Time, so having a time frame is probably important. Printed in China? No. 2001. So yeah, this book is actually older than I thought.
Okay, so we're talking about 50 years ago from
this point.
From this point.
Yes.
Okay.
Which is actually very recent in terms of
no, and I'm gonna get to that. I wanted that before I make a statement that I'm gonna make at the end of this.
I was re-listening to. I don't know. People have their opinions on John F. Kennedy, but I was listening to his address at Rice University, and he goes through this very elaborate, and we can touch upon this more, I think, after I talk about quarks, but to set up for later. Sorry, I'm moving my microphone and I can hear it in my monitoring. He says, he basically condenses the course of human history in the time span of half a century. And it's only 5 years ago did we invent the wheel. in a half century. 50 years. Only 5 years ago did we invent the wheel. 2 years ago was like Christianity in terms of that. And it was like midnight on December 31st at the end of this half century was when they actually went to space. Which is just crazy to think about. So like in terms of the scientific calendar, 30 years ago is not that. I mean, it's quick. That's
no, absolutely. 50 years and 50 years ago is not not long ago. But read about quarks, and then I'm going to get to a statement.
But yeah, so they thought that neutrons and protons were elementary, but like I said, you can just smash stuff together and get smaller stuff. And these particles that came out of that were named quarks by Murray Gell-Mann, who won the Nobel Prize for his work on them. The origin of the name, just for anyone who's curious, is an enigmatic quote from James Joyce of 3 quarks for muster mark. The word quark is supposed to be pronounced like quart with a K, to anyone who is reading the book, and I just realized that I said it out loud, so I didn't have to read that part. So what's weird with quarks is they describe them as having 6 different flavors, and that's the actual scientific word, and they are up, down, strange, charmed, bottom, and top.
So now my new goal in life is just to become a strange quark.
The first 3 flavors had been known since the 1960s, but the charmed quark was discovered only in 1974, the bottom in 1977, and the top in really like late in 1995. And yeah, like each flavor comes in 3 colors. There's really weird. I don't know who came up with all of this stuff. Like, I don't know if it was Murray Gell-Mann who decided all of these different namings, but yeah. He even notes it is quarks are much smaller in wavelength, much smaller than the wavelength of visible light, and so they don't really have any color. It's just that modern physicists seem to have more imaginative ways of naming particles and phenomena, and they no longer restrict themselves to Greek. And so a proton and a neutron are made up of 3 quarks, 1 of each color. A proton contains 2 quarks. 2 up quarks and 1 down quark. A neutron contains 2 down and 1 up. And then he goes further into all of these different things. So you can create particles made up of the other quarks: strange, charmed, bottom, and up and top. And they all have they have a much greater mass, and they decay very rapidly into protons and neutrons. So basically you can make other elementary particles that aren't the proton or the neutron. They just decay very quickly and become protons and neutrons, which are more stable. And yeah, so the quarks are the things that make up these elementary particles.
Right.
And so you start to get more
just started to even be aware of 50 years ago at the point of the recording of this podcast.
Well, okay, no. That was what was established. You have your laptop. Look up gold foil experiment real quick for me. Because I'm just to keep building this timeline. I believe that was 1880 something. The gold foil experiment.
1911.
1911. That was close.
Rutherford and his co-workers, Hans Grieger and Ernest Marsden. Okay, side note, Marsden, Marsden. I love that last name.
Marsden?
Like, I don't know why, but when I hear the last name Marsden, I'm like, I like it. Like, it's just it's a last name that I associate with good feelings. I'm a weirdo. I understand that. Yeah, but 1911.
Yeah. Yeah, because he says in the 19th century, when the only particle energies that people knew how to use were the low energies of a few electron volts generated by chemical reactions such as burning, it was thought that atoms were the smallest unit. Turns out it's not true.
Okay.
But yeah, that was 1911 to then 50 years ago from today, which was 70s.
Yeah. So let's
70s was 50 years ago.
Yeah. So I'm gonna create an even crazier time frame for you right now to put this into context.
Mm-hmm.
Okay.
Our table of context.
A table of context. When did you come and visit me in Florida when I lived there?
2017.
2017. That's when you bought this book.
Yeah.
New.
Yeah.
So it was printed in 2001, correct? Mm-hmm. So this book was still in circulation 16 years after Hawking is making this 50-year-old statement,
yeah.
right?
Yeah.
Okay. No, this is the crazy thought that I just had as you're talking about this. And as we talk about science, that means that when I was, not to age myself, but you like it when I do, when I was in high school taking biology, chemistry, and environmental science and learning, when I was in high school learning about atoms and protons and neutrons, the books I was learning from probably were not taking into account that what you just said about protons and neutrons not being particles.
Yeah.
That's crazy.
Yeah, because you were reading textbooks that were written probably before that was like established. That was probably something that was just theoretical. That someone said like, "Oh yeah, there's this experiment that's going on."
Right.
Yeah. In the foreword of the book, I don't know if this was in your foreword or not. But
I read that foreword too before I gave it back to you.
As Nathan Myhrvold of Microsoft remarked, Stephen Hawking has sold more books on physics than Madonna has on sex, which is why the book was still in circulation for so long.
But so the point that I wanted to make in coming to all of that is kind of the quote that I wrote down from, I think, chapter 11 that I really liked, that I think really was a good summation. It was a good end cap to the book itself, is that Dr. Hawking says that theories are always being changed to account for new observations. They are never properly digested or simplified so that ordinary people can understand them. And that's science. Like, before we started recording, we talked about the idea of the first law of thermodynamics, and that most people, up until a certain point, because poor education and everything, most people have either heard of the laws of thermodynamics, or if you say, have you ever heard that matter cannot be created nor destroyed? Most people are going to be like, yeah, absolutely. But see, that's a distillation of a scientific principle that has been proven and distilled and digested, as Hawking is saying, for the masses to understand.
Right.
A lot of the things that we're talking about in this are maybe ideas that are 50 years old, maybe. But what's happening is that they were conceived of 50 years ago, and then 5 years after that, a new observation is made as people are testing these things, and they tweak the thing a little bit, and then they move forward from there, and then a new observation is made, and then they tweak it again, and they move over in there. And so because these theories are always being changed because they're being tested, that's why there's so many scientific specialities. And that's why general
I think it's
science,
less though that they're being changed. I think it's more so that there are new additions being put forth.
No, that's what I mean by change. I mean change the way that you change a piece of steel into a sword. Is it's still the same thing, but it's being refined and added on and detailed out. And because of that, there's not a chance for them to take it to the 9th grade textbook.
Right.
And concretely write it down the way that you've written down, like, gravity is a thing. Or that, matter is not created or destroyed. Like, it's just all moving so quickly.
Right. Fun fact, though.
To this.
Who do you think one of the earliest pioneers of relativity was? If you were to take a guess. I'll give you a hint. It's not Einstein.
Was it Galileo?
Yeah, it was Galileo.
Yeah, it's the only other scientific dude that I know.
Yeah, he because back in the day, in Italy and whenever he was alive, I don't remember the number. It was hard to think of this idea of things being relative, but he basically said, what if you were in a boat traveling on the ocean and you were below deck? how would things be traveling relative to you? Right. That was one of the ways that he postulated.
Listen, not for nothing, like we talk about all of the advancements in science. Galileo
was a smart dude.
Was crazy. Could you imagine the things that Galileo would have come up with if he had lived in a time where he had more at his disposal? They talk about it in the first chapters in there, and like a lot of Galileo's early theories he published under an anonymous name because he knew that they were so contradictory to the accepted on the back of a giant turtle type things that the community believed.
I guess we should like give some sort of explanation as to what that means.
That it's turtles all the way down.
That it's turtles. Since you didn't know what that was until you read this book.
And since then, even before reading this book, since you said it to me without context, I've heard it in at least 2 other podcasts, also with no context given, one of them not even having anything to do with science.
It's the very opening of the book.
It is
a well-known scientist, some say it was Bertrand Russell, once gave a public lecture on astronomy. He described how the Earth orbits around the sun, how the sun in turn orbits around the center of a vast collection of stars called our galaxy. At the end of the lecture, a little old lady at the back of the room got up and said, "What you have told us is rubbish. The world really is a flat plate supported on the back of a giant tortoise." The science gave a superior smile before replying, "What is the tortoise standing on?" The old lady says, "You're very clever, young man, very clever, but it's turtles all the way down." It's turtles all the way down.
It is turtles all the way down. That's probably a good ending, please.
I can talk a little bit more about some stuff. So one of the things, I guess one of the side notes to add, with like the specializations and stuff.
Yeah. That's where I'm going too. So,
to anyone I know, listen. I feel your pain. To people who are normal people listening to this, I feel your pain. Math sucks. Math is one of supplemental writing or supplemental reading that I like. There's a paper called The Mathematician's Lament, which is written by a professor or teacher, I don't remember, but an educator
if you
of
find
mathematics.
It, you should put it in the show notes.
I have it saved on my computer. I can add it. That's actually what the show notes are going to be. So the show notes are probably going to be, because you normally do a sources page for this.
Yeah.
It's going to be a lot more of just like supplemental reading.
I think that's a good idea.
I'm going to put that on there. I'm going to put the Feynman lectures. I'm pretty sure you can get the Feynman lectures online for free, released by Caltech. If you want to learn physics, the Feynman lectures are a great place to start.
Mm-hmm. I'll send you the article on Time that Karen sent me.
Yeah, you can add that there too. But yeah, The Mathematician's Lament is basically this dude who's writing, and he's like, imagine you're a music teacher, right? And you wake up in a cold sweat, realizing that we have to prepare the kids for a world that's ruled by music. We have to make sure, like all of these different pressures that are put on the teachers to teach students about music, and basically comparing that to what math is, and saying this is we're butchering math because math is an art. It really is. I believe that. I just believe it's.
I can agree with that.
Very well mistreated. Not everyone is going to want to learn to draw. That's fine, but there is an art to drawing. There's an exploration to drawing. There's a way for you. One of the things that because I'm weird, in my spare time, I decided to figure out where the formula for compound interest comes from. It was just a thought that I had, and I was like, where does this come from? And so I just tried proving it, and I did. And it was so satisfying to be like, oh, I just got from point A to point B. This is this well-established fact that I've been told like my entire life of what compound interest is, and I just proved that this is how to find it from absolutely nothing, from just knowing like the simple fact of if I start with some amount of money and I add a percentage of that amount of money to that total, positive or negative, right? Like what does that mean? And I don't know. I feel like if you can have that kind of like of math and understanding of math, lots of physics concepts will make more sense. Math is the heart of physics, for sure.
Yeah.
And while there are lots of theories there are lots of new things coming out that people are discovering. If you have any kind of understanding of mathematics, it will be more digestible. Like the specifics and like that hand waviness will start to go away a lot, because you'll be like, oh, this is just like XYZ. Even if I don't understand like how to do these integrals, I know where these integrals came from, or where this wave function comes from, or why Professor Hawking is using these imaginary numbers here.
And we were talking about this before we started recording too, is that math is an integral part of the natural world.
Yeah.
Like
you can get far in life by just knowing math and history.
Yeah, that whole thing that you were saying about like the music, the music teacher thing.
Yeah.
Is true. Like, and we laugh at it, is that, yeah, that sounds ridiculous. And yes, I get what you're saying as math being an art form more so than something that's concrete. Like you have to, there's a beauty in it that you have to appreciate in order to be passionate about doing it. Mm-hmm. However, the world isn't run by music. The world is very much, I mean, there's math everywhere.
Music is just math, Victor.
I know music is just math. I knew you were going to say that. Anyway, but we were talking about geometry, just geometry in and of itself. Like, outside of the science, like, geometry is in environmental science, and geometry is in biology and anatomy. Mm-hmm. Everywhere. Like, that's how your skeleton doesn't collapse under the weight of your flabby muscles. Mm-hmm. Like, it's geometry. Mm-hmm. That's how all of it works. That's how bees operate.
Yes.
Listen, there's
a really funny TikTok that I saw. Speaking of physics and bees, and time. There's a really funny TikTok that I saw of this dude who was talking about like how we discovered that bees perceive time.
I'll have to look that up.
I will go on TikTok on my computer when we're done this. I'll even add it to the sources. Damn it!
Add it to the sources.
I'll add a link to it.
But anyway, the last thing that I had, which was a statement that I appreciated in his conclusion chapter, aptly called Conclusion.
Yeah,
loved. Mm-hmm. Or no, sorry, it was called Conclusions. It was like, yeah, it's very scientific.
Was it multiple conclusions or was it a single conclusion? I gotta fact check this.
Yeah, you can fact check me. Maybe it was a mistype in mine.
It's only one conclusion.
Because mine, I'm pretty sure
there's not multiple conclusions, Victor.
Conclusions. Well, you could come to conclusions. Anyway, he talks about how, again, I don't remember the exact quote, so I'm going to paraphrase it, that the sciences used to be the realm of the philosopher. But since science has gotten so complex within just the last, we'd say, like 75 years, something like that, mm-hmm. with all of the different specialities and, you know, sub-focuses, you know, he's talking about how even those who study a specialty in science 2 years after they graduate from, he said university, but school, right?
Uni.
That their study is all old news, just 2 years, two to 3 years later, right? So philosophy has been left as just a study of words, which is a shame. I liked how he ended with kind of this aside note, because it completely contradicted the thing that he stated in the beginning in chapter 4, was that Hawking, I think truly in his own admittance, admits that there is a place for philosophical thinking within sciences, that they shouldn't be completely devoid of each other. And if you look at Socrates and Aristotle,
there's a reason why the Greeks were pioneers.
Right. There's very much logical thought in their philosophical thinking, and they do talk about the science that runs the world within their philosophical constructs. So I like that they're not two. I've never viewed them as two separate disciplines. They need to be talked with one another. It's like what I've always said, like, I would love to study, if I had to go back to school, I would study philosophy, psychology, and sociology. And I wouldn't be able to do anything with that degree, but with those three studies under my belt, I would have the best understanding of the human being that you could get.
Yeah. you would have a good understanding, a very accurate understanding of the human condition.
Right. And I feel like philosophy and science are also tandem studies as well.
I'd say that just in terms of like sets, they both belong to the set of answers. They're both seeking answers. They just have different means of getting there. Or like they've slowly diverged in the means over time. Like they both started off on the same road going towards answers, and then like philosophy took a branch west, and science took a branch like east, and they've been kind of bending around, still going the same direction over time. It's like one took 95 straight through DC, the other one took, was it 395 around the loop?
So speaking of taking 95 right through DC, that's a really good segue.
I know, it was a really good segue.
You and I are getting ready to get on 95 to drive through DC to head towards Richmond, Virginia.
Yeah.
Which is why we are not streaming this episode, but instead recording it for publication later.
Yeah, the next couple weeks are going to be weird for us. We're also going to start streaming on YouTube more. That's something that's new, just because we wrapped up the episode, or as we're wrapping up the episode. This podcast is going to be up. We're going to have another podcast next week. We're not going to be streaming again next week because things are weird. You have a wedding to go to. The week after that, there's more stuff that's weird as you get ready to move.
So we'll probably be streaming, but we'll probably stream earlier as opposed to later in the day.
Yeah. Or we're just going to do recordings. I don't know.
Yeah, we'll figure it out. But you know what you should do is you should follow us on Spotify and
the socials.
Socials of Realm of Logres and
they'll all be linked and you have access to them places. I'm going to be good, and I'm going to put that stuff on Twitter so you know the deets.
Sounds good.
Because I've been not great with that.
That's all right. I completely didn't post last week on Instagram when we posted our new podcast.
We're learning. But yeah, thank you. We will be back next week, and I hope you guys have a great day.